Hi everyone, welcome back to part 2, chapter 1.3. In this video, we are going to discuss about Arrhenius equation. At the end of the lesson, you should be able to state Arrhenius equation, explain the relationship between temperature and activation energy to the rate constant based on Arrhenius equation. Then determine the rate constant K, activation energy EA, temperature, and the factors A using Arrhenius equations by calculations and the graph. So for this Arrhenius equations, it shows the relationship between temperature and the activation's energy to the rate constant. So which is represented using the formula over here, whereby we have this K equals to A, this E represent exponent, to the power of negative EA over RT. So for this case, is our rate constant. So this rate constant normally will be given or provided in the questions. So the rate constant again follow the order of reaction. And now we have this R, which is your universal gas constant. All right, so this R, we are using 8.314 joule per mole per Kelvin. Okay, since we are using the activation's energy, so we're using this value for R. E is the exponent, T is the absolute temperature, and it must be in Kelvin. EA, activation energy, and lastly, A is your frequency factor. So the frequency factors is like a constant, so it will be given in the questions or asked to find the frequency factors. Okay, so next we want to look at the relationship between temperature to the rate constant. So the higher the temperature, the larger is the rate constant, and therefore you will have a higher rate of reaction. So the reactions rate increases. So this to make sense because higher temperature, we will expect a faster reactions rate. And next one is the relationship between activation's energy and the rate constant. So larger the activation's energy, you require more energy to overcome so that the reactions can happen. So larger activation's energy, it will result in a smaller rate constant, which will refer to a lower reactions rate or the rate of reactions decreases. So bear in mind of the relationship between two of these factors. So beside temperature, which can affect your rate constant, activation's energy can also affect your rate constant. So Arrhenius equation, using the formula just now, we can use that formula to plot a graph. And from that graph, we can determine our activation's energy. So learn the whole Arrhenius equation. So this one refers to learn. So that means you learn the whole equation, it will become like this. So ln K equals to negative EA over RT plus ln A. So we try to rearrange a little bit so that you can get your y-axis. Okay, your gradient. So gradient M equals to negative EA over R. So we know that this is a negative slope. X-axis, we have our 1 over T, and then the intercept is ln A. And then using this equation, we need to draw a graph of ln K against 1 over T in unit per Kelvin. And it looks something like this graph. So ln K against 1 over T with the unit per Kelvin. Ln K doesn't have unit. Now in this case, ln K doesn't have unit. So this intercept is our ln A. And the slope M equals to negative EA over R. So if you plot the graph, you can calculate for its gradient. And the R, the universal gas constant 8.314, then you can find the activation's energy. So here is the example questions. The following reaction is first order with respect to NO2 and zero order with respect to O2. So NO2 raised to power 1 and then O2 raised to power 0. Okay, so write your red law. So in this experiment, the rate constant was determined at different temperature and the data was tabulated. So using the data below, you need to plot a graph. Okay, so write the red law of these reactions and determine graphically the activation's energy EA in kilojoule per mole for the reaction. So when you look at the questions, determine graphically. That means the questions ask you to plot a graph. Okay, determine graphically, you need to have a graph. From the graph, determine the EA. Alright, so draw another table. For the K, you need to calculate for ln K. For temperature, you need to calculate for 1 over T, the unit per Kelvin. Alright. One more thing. If the questions give you in degrees Celsius, you need to convert into Kelvin also. So convert into Kelvin, then after that convert into 1 over T per Kelvin. Okay, with the unit per Kelvin. Alright, so from the informations given from your questions 1, we have the order with respect to NO2, which is first order, and 0 order with respect to oxygen. So this is your rate law. And then from your table 1, using the data, you need to create another table, okay, in which you have your 1 over T, and the unit is per Kelvin, and K becomes ln K. Why we are using ln K and 1 over T is extract from the equations here. So after you learn your Arrhenius equations, so you have your ln K, negative EA over R, and then in bracket you have 1 over T plus ln A. So this Y is your y-axis, ln K, and then you have your x-axis is 1 over T, and the gradient is the same as negative EA over R. And this ln A is your intercept. So when you're calculating, you will see 1 over T, 1 over 477, for example, you get the value around 2.1 times 10 to the power of negative 3. And similarly for the rest of them. So I just put this 10 to the power of negative 3 together with the units. Okay, it makes it easier when you want to plot the graph. Okay, easier for you to find the scale. So please try to plot the graph using the informations here. So when you plot the graph, you will see a linear graph like this. So in this graph, we have our title, graph of ln K against 1 over T. We have our y-axis, ln K, our x-axis together with 10 to the power of negative 3 and the units. And look over here. Because the scale is too small, so I cut the graph and from 0 straight to 1.5. And then carry on is 1.6, 1.7, and so on. So that means if you put this thing, you cut the graph, you cannot do intersect. Okay, please don't draw the intersect. That means over here, you don't have the intersect with y-axis if you want to do this one. Okay, so after you plot this 4 of the points given, you will find a straight line. So this straight line, maybe it will not fall exactly onto the points, but you need to try to find the best fit line. Best fit, it means it will link to most of the point and it's balanced. So if you look at this straight line, this is a best fit where I have 2 points sitting on top of this line and 1 point slightly deviate above and 1 point slightly deviate at the bottom. So it is quite balanced and it is the best fit. So from the graph over here, first of all, title, you have 1 marks. Okay, and you have your axis with the correct unit, you have your 1 marks. When you have the point plotted, this marks is for the point, not for of the point. And when you have a straight line with the best fit, you got another marks. Okay, so next thing what we want to do is to find the gradient. Okay, because the questions want to ask for activation's energy. Okay, questions requested for activation's energy. So we want to find the gradient. So put your dotted line to find the gradient inside the graph. Okay, remember that when you find the gradient, try not to find it from the point itself. Okay, you can find the gradient from the straight line, any point, as long as you can find the number easily. Okay, so the gradient roughly about -1 to 66.67. And for this gradient, because ln K doesn't have unit and we have the unit for 1 over T is per Kelvin. So actually for this gradient, we have a Kelvin for its unit, but this is not important. The important one is the final unit for activation energy. So once you find the gradient, okay, we just match it with this formula. M equals to negative EA over R. This formula itself has 1 mark. Okay, and then you try to solve it to get this activation's energy, which will be in joule per mole. Since the rate constant, okay, for this gas constant, the value, okay, for this R, the value is at 8.314 joule per mole per Kelvin. So after you eliminate the per Kelvin, it left with joule per mole. So the answer, activation's energy over here, obtained straight away from this gradient, is in joule per mole. So if let's say the questions ask for kilojoule per mole, then you have to convert it into kilojoule per mole. So 105.31 kilojoule per mole. So which is your final answer over here. But if the question doesn't request, okay, it doesn't request for kilojoule per mole, both answer accepted. Alright, so another uses for Arrhenius equation is when we want to compare between two sets of rate constant and temperature. That means you have two value for rate constant, you have two value for temperature. Okay, then we can use this formula. So we have ln K2 over K1. This K refer to our rate constant. So you have two value for rate constant and equals to negative EA over R. So again, this R you have a value 8.314 joule per mole per Kelvin. Alright, and then one more important points over here, I'm going to use red color. Your activation's energy will be in joule per mole. Okay, remember, it will be in joule per mole. Okay, it is because of this rate constant, it is in joule. So if the questions give you in kilojoule per mole, you need to convert into joule per mole by multiplying with 1,000. Okay, and then continue with the equations 1 over T2 temperature, the second temperature for K2 minus 1 over T1 temperature for K1. So for this temperature, also important, madam will circle in red color. It should be always in Kelvin. So if if the questions give you in degrees Celsius, convert into Kelvin by adding 273 or 273.15. Alright, this is a very important unit. So make sure units are correct, convert when necessary to make sure that activation's energy in this formula, joule per mole, temperature in this formula will be in Kelvin. So given in the questions over here, we have the rate constant for first order reactions at 25 and 35 degrees Celsius. So over here you can see we have two temperatures. So let's just label this one as T1, this one as T2. Okay, and then you are given also the rate constant. So the first rate constant refer to the reactions at 25 degrees Celsius. So we label this one as K1 and we label the second one as K2. Okay, so determine its activation's energy in kilojoule per mole. Okay, remember that if you're using the formula, the activation's energy you will first get in joule per mole. And then after that, you need to convert into kilojoule per mole. So using the formula, ln K2 over K1 equals to negative. Okay, be careful of this negative sign. After you do your substitution T1, T2, K1, K2, and also the gas constant R, then do your simple calculations and you will eventually get your activation's energy equals to 101,950.67. Okay, so from these equations, you will get the activation's energy in joule per mole. Okay, it will be in joule per mole. So you need to convert into kilojoule per mole by dividing by 1,000. Okay, divide by 1,000 to get 101.95 kilojoule per mole. For example, questions 2, the gas phase reactions between methane and diatomic sulfur is given by the equation. So you have a balanced equation over here. At 550 degrees Celsius, the rate constant for this reaction is 1.1 liter per mole per second. Alright, so just to revise with you, this unit is a second order. Okay, it's a second order. Okay, you can refer back to the formula in capital letter M and then you do your substitutions, see whether you can get this units okay or not. Alright, and given the activation's energy is 144 kilojoules per mole, calculate the temperature in degrees Celsius at which its rate constant is 6.4 liter per mole per second. Alright, so do a little bit of information extra. If let's say I label this one is my T1, the 550 degrees Celsius is T1, and this 1.1 is my K1. And then this one is my EA. Remember that EA I need to convert into joule per mole. So that I can substitute into my formula. And then calculate this temperature is my T2, at which it has this K2. Alright, so applying your formula, ln K2 over K1, negative EA over R, 1 over T2 minus 1 over T1. So do your substitution, we have K2, we have K2, we have K1, we have EA. So this EA, be aware, 144 times with 1,000. Okay, and then do substitutions of R 8.314, 1 over T2 minus 1 over T1. So T1 convert from degree Celsius into Kelvin. So you get 823.15. And then solve your mathematics equations. And you will get your temperature in Kelvin. So from this formula, you will get your T2 in Kelvin. Then you have to convert back into degree Celsius since the questions request in degree Celsius. Okay, so use this 898.47 minus 273.15 to get this value. Alright, so that's the end of our chapter 1.3 and the end of our chapter 1. Please attempt the exercises given in the notes.